This is the second half of Lecture 10, and in this one we're actually going to try some problems involving spectra. So I'm starting with just a quick review of what we just finished in the first half of the lecture. Remember that when we do a spectrum problem, we're going to find the energies of the two levels if we don't already know them. Sometimes we're going to know them already. They may be given. They may be hydrogen, so we've done them so many times we don't need to do them again. But if we don't know them, we'll find them. We subtract those, and that becomes equal to the energy of the photon. So whatever that difference is between the levels, we can set that equal to HF, and we can solve for the frequency, and then we could figure out the wavelength. So we're now going to try problem 23 in your packet. And we're only going to do part A. You're going to do part B on your own as part of your assignment. But we're going to do several cases here. So I'm going to do several calculations for this one. What we're trying to do is find the energies and then the corresponding frequencies and wavelengths between the ground state and the first three excited states. So we're going to do n equals 1 to 2, and then n equals 1 to 3, and then n equals 1 to 4. Now, I'm going to assume in this one that we actually already know all of those energies. We've done hydrogen several times, and I'm not going to sit there and do the math again because that would waste our time. But if we didn't know them, we could figure them out using the E equals 13.6 times 1 minus 1 over n squared formula that we did previously. So just to remind you, the energy for the ground state is always going to be 0. The energy for the first excited state for hydrogen is 10.2. For the third excited state, it's about 12.1. And for the fourth excited state, it's about 12.75. So the first one that I'm going to do is I'm going to do 1 to 2. So what I do is I first subtract my energies. Now, in this case, that's very easy. It's just 10.2 because one of the energies is 0. When you try your own, though, you'll have a little bit more complex subtraction, not that even that is going to be very hard. And I can set that energy equal to the energy of the photon, which is, of course, equal to HF. So I can say that 10.2 is, excuse me, pausing for a second. I'm continuing again now. I'm sorry I had to pause for a minute there. My pen stopped working. Where we were was we were saying that the energy is equal to HF. So I can say that 10.2 is equal to HF, and I can solve for the frequency simply by dividing 10.2 by H. Which gives me a frequency of about 2.5 times 10 to the 15. And then if I want to find the wavelength, well, I know that v is equal to lambda f, and since this is light, the speed is equal to the speed of light, c. So I can just solve for the wavelength, which in this case is 1.2 times 10 to the negative 7 meters. That's about 120 nanometers, which is ultraviolet. In fact, all of these are going to be ultraviolet. So now I'm going to do the same process for the transition from level 1 to level 3. I can say that the change in energy is equal to 12.1 minus 0, which is 12.1. And I can set that equal to HF. And this time I get the frequency of 2.9 times 10 to the 15. And then I do V equals lambda F. My speed again is the speed of light. And this time I get a wavelength of 1.0 times 10 to the minus 7. And then finally, we'll do 1 to 4. Change in energy this time is 12.75 minus 0, of course it's 12.75. Giving a frequency this time of 3.1 times 10 to the 15. And then a wavelength of, this time, 9.7 times 10 to the negative 8th. Notice that my wavelengths are getting smaller and smaller, my frequencies are getting bigger and bigger. As I deal with jumps between levels that are more and more spread apart, I'm dealing with more and more energy. So I have bigger frequency as well and smaller wavelength. Our next question, which is number 24, is a problem from your textbook, which is 5.44. It's actually not going to involve a lot of math, but it will help us remind ourselves of what is absorption, emission, things like that. So it gives us the diagram of the energy levels of a hydrogen atom. Once again, it's those same energies. And the version that I'm able to copy has all of this information in it, but the one in your book doesn't. So that's just what I'm able to copy. And we're going to start with which transition represents an atom that absorbs a photon of 10.2 electron volts of energy. Well, absorption means you're gaining energy. So that means if I'm gaining energy, I must be going up in level. So that could only be, these were labeled, no, actually you have different ones labeled in your book. I'm sorry, not paying attention, but the one you have labeled in your book, one that looks like this is an absorption where it's going up in level. It happens to be the case that that one is B. And then emitting 10.2, it's got to go from 10.2 down to 0. So it's one that looks like this. We're losing energy. So the one that looks like that is C. One that has an electron that's breaking free means it ends up going higher than that 13.6 level. So that's one that looks like this, and the one in your book, that is E. One that's not possible is one that does not end up in an allowed energy level. If you don't end up in an allowed energy level, the transition is not possible, something that looks like this. And the one in your book, that is D. And then it asks about transition A, which is a transition from level 3 to level 1. And so first it asks, is that absorption or emission? And since it's going down in level like that, it's going down in level like that, it's losing energy, so that must be emission. And then it asks, how would the wavelength compare to the one involved in transition C? C is one that looks like this, and this is what A looks like. Now, C is going to involve a smaller energy. Because it's going from 10.2 down to 0. The energy of C is 10.2, whereas the energy of A is 12.1. So since C has smaller energy, it also has smaller frequency. Because if you've got smaller energy, you've got smaller frequency according to E equals HF. And if you've got smaller frequency, that means you have bigger wavelength. Useful trick to know is that the smaller the jump is, in something like this, the smaller the jump is, the bigger the wavelength is going to be. So when you are transitioning in between two very closely spaced levels, like say those two, you're going to actually end up with a much bigger wavelength than when you do a really big jump like one like in A. So the closer the levels are, the bigger the wavelength is going to be.